Okay, everybody, we are going to talk a little bit about what nuclear chemistry is. You've already been exposed to several readings and some videos in regard to what nuclear chemistry is, so you already have a good idea, but what I want to talk about today is nuclear reactions and nuclear decay. So let's get started. You should have a PowerPoint on Google Classroom, so if I go too fast, you'll just need to go back. And it is very important that you put this information into your notes because your quest or test / quiz that you'll get over this information is open note, but you can't use any worksheets or anything like that. So make sure that you bulk up your notes. So if I go too fast, then go to Google Classroom and make sure that you copy everything down. So first of all, like this says, nuclear chemistry, we're focusing on the nucleus of an atom. It's the study of the changes and reactions that occur inside of the nucleus. So the whole idea behind chemistry and atoms is stability. Okay, so some atoms want to combine with other atoms to become stable. Some nuclei will break down and change so the atom can become stable. So the whole theme here is stability. So different types of reactions in chemistry. We haven't talked about chemical reactions yet, but you have chemical reactions, and that's when atoms gain, lose, or share valence electrons to make compounds or molecules. And that makes atoms stable. The other type of reaction is nuclear reactions, and these are, of course, like it says, reactions that occur inside the nucleus of an atom. A lot of these atoms' nuclei will break down or will change because their nuclei is very large, and the bigger the nuclei of an atom, the less stable it is, and so if it can break down and become more stable, it's going to do that. So when we talk about radioactive decay, this is when some sort of unstable atom is going to undergo a change, and it's going to release energy or matter, or both, from the nucleus, and it's going to do this to become stable. So when we talk about nuclear radiation, we're talking about the matter and the energy that comes from the breaking down of a nucleus that's unstable to form a more stable nuclei. Okay, so let's talk about several of these. Okay, so there's 4 types of radioactive decay we are going to talk about. Alpha decay, beta decay, positron emission, and electron capture. Each of these decays or emissions or captures are going to break the nuclei down. It's going to change the nucleus into a different type of nuclei or a different atom so that atom is stable. You guys had a little bit of a reading a few days ago over half-life. Half-life is the amount of time it takes for half of a radioactive sample to decay, and each element is going to be different. Carbon-14 takes 5,715 years to break down, and it undergoes beta decay. We'll talk about that in a second. Uranium-235 breaks down, okay, or half of the sample will decay after 7.04 times 10 to the 8th years. So there's a very, very large half-life for uranium-235, which you'll be able to understand once you see some information about Chernobyl and why the area is still contaminated, because uranium-235 takes a long, long time to decay, so it's actually safe. Iodine-131 decays in 8.1 days, and it undergoes beta decay. Okay, so again, half-life, the time it takes for half of a sample of radioactive atoms to decay. Okay, so let's talk about alpha decay. Alpha decay is a type of nuclear reaction, or it's a type of decay. This is what happens inside of the nucleus. 2 protons and 2 neutrons leave the nucleus of an isotope. Those 2 protons and those 2 neutrons leave in the form of an alpha particle. Right here, alpha particle. An alpha particle is literally just like a helium atom. Right here. Okay, so 2 protons, 2 neutrons. Okay, that represents our mass number right here. And then this is, of course, our atomic number. So this is what happens inside of the nucleus. 2 protons, 2 neutrons leave in the form of this helium isotope. Energy leaves the nucleus, and that is going to change the original isotope's mass number and atomic number. So what happens is the mass number is going to decrease by 2. Oh, let me try this. Okay, so the mass number is going to decrease by 4, and the atomic number is going to decrease by 2. That kind of makes sense, because if you have 2 helium and, if you have 2 protons and 2 neutrons leaving the nucleus, that totally makes sense, because the mass number is a combination of protons and neutrons. And then if you have 2 protons leaving, of course your atomic number is going to go down. Okay, so when it comes to alpha decay, these reactions, you always start with one single reactant, okay? And it's some sort of radioactive isotope, like 230, uranium-238. So let me see if I can draw on my screen here. Let's try. Okay, so this is how the reaction works. That should be an arrow, but it's not. Okay, so in alpha decay, we have this one single reactant, our radioactive isotope. We are going to draw, let me try again. My computer's giving me problems. Okay, I'm going to draw my produces arrow. There we go. And I'm going to fill in my product. So in alpha decay, every single reaction produces an alpha particle, which is this helium. My stylus is not being good to me. It is going to produce this helium. Okay, let's try this again. It's going to produce this alpha particle, which is a helium atom. And it always produces that, always. And it's going to produce some other isotope, a more stable isotope. So we have to do a little math and use our periodic table. So we know that the mass number decreases by 4 and the atomic number decreases by 2. So I'm going to do my math first. So my new mass number is 234 and my new atomic number is 90. So now, oh geez Louise, look at that. So 90. So I have to go to the periodic table. I have to find which element has got atomic number of 90, and that is thorium. So TH. So basically what we're doing is we are given a radioactive isotope, and we're going to predict the products. Okay. In alpha decay, in an alpha decay reaction, we always get a helium or an alpha particle, and we get some new, more stable isotope. And I would suggest you work each one just like that. So let me see if I can get my stylus to work again. There's my arrow. It is going to produce a helium ion, or helium isotope. So my helium isotope 4, 2 plus, this might not work. I might have to do something else here. Okay, sorry about that, technical difficulties. Let's try this again. Let's look at radon 222. We are going to draw our arrow. This is my only reactant. I know it's alpha decay, so automatically I have a helium isotope or an alpha particle that is produced, plus some new isotope. So it's alpha decay, and you'll always know what sort of decay is occurring. So 222, I'm going to decrease that by 4, so that's going to be 118. And my new atomic number is going to be 84. So I'm going to go to my periodic table, and I'm going to figure out which element has the atomic number 84. And that, of course, is polonium. So I'm going to make that PO. So in every alpha decay reaction, you start with an unstable isotope, and you produce an alpha particle and a new, more stable isotope. So let's try this again. Okay. I'm going to do my arrow. I'm going to start with my alpha particle, so He. I'm going to put my 4, I'm going to put my 2. Now I'm going to do a little bit of math. 210 minus 4 is 206. Atomic number goes down by 2, so that's 82. Ugh. I have to do something else for the rest of them. My mouse is not working. Atomic number 82 is going to be lead. PB. Okay, I'll be back for the rest of them.